Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. You're designing something that requires a shunt resistor or a current sense resistor, and you just don't want to wait for the off-the-shelf resistor to arrive. Or maybe you want a specific value that just isn't available anywhere. Or maybe you just want to do it yourself for fun. In this video, I'm going to show you how to create your own low-value resistors using stuff you either have hanging around your shop or you can buy at the local hardware store. It's as easy as can be. If you have questions or comments, make a point to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe to the channel. All right, let's dive into making some homegrown resistors. The basis for this entire process is that all conductors have resistance associated with them. The smaller the conductor, the more DC resistance they have. At the same time, the less current they can safely carry. So what are we going to be doing? We will be selecting the right wire size for the application, calculating the length of the wire that we need for the target resistance value. Then we will be measuring and adjusting our wire length to achieve our goal. And then finally, doing final assembly and packaging and final testing of our resistor. Let's start this design by choosing the right wire to choose. The target values that I'm about to discuss came from my video on adding adjustment to your ammeter. The link to this video is up in the corner for you here and down in the description. Now, let's go choose our wire. The first thing that we have to do is establish a target value for your resistor. For this exercise, I am shooting for 18 milliohms. The next thing is to determine the maximum current that is going to be potentially flowing through the resistor. My application is for a shunt resistor for a 5 amp ammeter, so my current will be 5 amps. Now we multiply this value by 2, so 2 times 5 is 10 amps. Now that we have this value, we have to look it up in our wire table under the maximum amps for chassis wiring. We are looking for the smallest value that is greater than or equal to the value we just got. So we follow this down until we find something that is, here we go. See, 11 amps is just a little bit greater than the 10 amps that we have found so far. Now, if we follow this row over to the left, we discover that what we need is some 20 gauge wire. Well, after a fair amount of looking, I did find a nice roll of 20 gauge solid copper wire to use. If I didn't, I'd either have to go buy some or use the next bigger size that I did have. Once we have settled on a wire size, we need to know how much resistance our wire has per unit length. To do this, we follow the row across until we come to one of two columns: ohms per 1,000 feet or ohms per kilometer. So we find that 20 gauge wire has 10.15 ohms per 1,000 feet. It also has 33.292 ohms per kilometer. Now we're ready to begin calculating the wire length we need for our resistor. So far, we have an application current of 5 amps. Our target resistance is 18 milliohms. We have discovered that we need a wire gauge of 20 gauge wire, and the resistivity of our 20 gauge wire is 10.15 ohms per 1,000 feet, or 33.392 ohms per kilometer. The calculation of the needed wire length is simple and straightforward. The first thing we have to do is calculate the ohms per inch or the ohms per centimeter for the selected wire. So I have 10.15 ohms per 1,000 feet. And there are 12,000 inches in 1,000 feet. So we simply divide our ohms per 1,000 feet by 12,000 to find the ohms per inch. And so we have 10.15 ohms per 1,000 feet divided by 12,000 gives us 0.84583 milliohms per inch. Now, if we're using the metric system, there are 100,000 centimeters in a kilometer. So to get the ohms per centimeter, we divide the ohms per kilometer by 100,000. And so we have 33.392 ohms per kilometer divided by 100,000 gives us 0.33292 milliohms per centimeter. Now that we know the ohms per inch or the ohms per centimeter, we know the target value of our resistor, we can calculate the length of the wire we need. To do this, we simply divide the target value by the ohms per unit length value. The resulting number will be in inches or centimeters. So in my case, we have our target value of 18 milliohms. We have our ohms per inch of 0.84583. We do the math, and we get 21.281 inches. If you're in the metric system, we have the same 18 milliohms. We have milliohms per centimeter of 0.33292. We do the math, and we get 54.067 centimeters, or 540.67 millimeters. Well, wire resistivity is not necessarily absolutely dead on according to the tables. This calculation gets us within the ballpark. Furthermore, we're going to need some additional wire to allow us to connect it to something. For this reason, I recommend that you cut the wire long by no less than 1.5 inches or 4 centimeters. You can always cut the wire, but you can't make it longer. So I am going to cut mine to 22 3/4 inches, or around 580 millimeters. Now we're ready to go. So what are we going to need to do this? Well, let's see. We're going to need a power supply with sufficient voltage and current capabilities. We're going to need an ammeter to measure the system current. We're going to need a millivoltmeter to measure the voltage drop across the resistor. And we're going to need a load resistor. Now, as we plan our testing scenario, we have to remember that the accuracy of the resistance value is totally dependent on the accuracy of the test equipment used to measure and adjust that value. You have two pieces of equipment involved in this measurement. You have the ammeter and you have your millivoltmeter. Now we need to choose test parameters and equipment to minimize measurement uncertainty. The more accuracy you need, the more you will have to scrutinize the tolerances of your test equipment to ensure the highest possible accuracy. Now suppose we shoot for 100 millivolts with an 18 milliohm resistor. That means that my test current is going to be 5.56 amps. Okay, so I pulled the number out of the air. Now I have a Fluke 179 DVM and a Tenma DMM. Which measurement device will give me the best accuracy for these measurements? To answer this question, I need to go through the accuracy calculations to determine the best combination. If you're unsure about how to do this, check out my video on the subject. I've put a link for it up in the corner here just for you. Having done all of the accuracy calculations, I've discovered that my greatest accuracy will be if I measure the voltage with the Fluke and the current with the Tenma. This will give me a total measurement uncertainty of plus or minus 3.13%. Now that we have this established, we can turn our attention to getting things set up for the test. I will begin with the load resistor. Well, what value do I need? Well, this will depend on the voltage I choose for the test. Now we've already established that we're going to be testing using 5.56 amps. Okay, so now I'm going to pull another number out of the air. Let's say we're going to use 20 volts for our test. This means that the load resistor needs to be, well, let's see, 20 divided by 5.56 gives me 3.6 ohms. My load resistors are only rated at 5 amps, and I want to put 5.56 amps through them. I don't want them heating up. So I've decided to put them in parallel, set each of them for 7.2 ohms. High precision in setting the load resistance value is not necessary. The goal here is to get our current in the vicinity of 5.56 amps. Measure the current through our resistor, measure the voltage drop across our resistor or our wire, and then we can calculate its actual resistance from that. What we're going to be doing here is measuring the resistance of this piece of wire using what is known as the Kelvin or 4-wire connection. For a detailed discussion on how to do this, see my video on this subject. I've put a link for it up in the corner up here. Now, we're ready to go to the bench and get things set up.
Before we begin, we need to be sure that the load resistor is set at the right value. Notice here it is set to 3.6 ohms. We need to make sure that the power supply voltage is turned all the way down and that the current is up high enough to make sure that we can get the current that we need in order to accomplish our goal. We need to make sure that the ammeter is set to the right scale. We're down here on the 10 amp scale. We're plugged into the 10 amp terminals, and that the voltmeter is set to the right scale. We're here on the millivolt scale on our voltmeter. As you can see, we're all connected up and ready to go. Notice that the resistor is nothing more than a wire on the bench. We have our current connections out here, and we have our voltage connections in here. Now that we're all ready to go, we're going to turn on the power supply, and we're going to begin increasing the voltage here while we watch our ammeter. Our goal is 5.56 amps. And when we get there, here we go, 5.56. There's 5.55 with 106.5 millivolts. 5.55 amps with 106.5 millivolts gives us 19.19 milliohms. As you can see, it's a bit high as expected. So we're going to reduce the amount of wire between the voltage clips and repeat our test. As you can see, all I did was strip off a little more insulation and move my voltage clip back here. I did it on both ends. Now let's see how this performs. Now we have 5.58 amps and 100.7 millivolts. This gives me 18.05 milliohms. This actually took a few iterations of stripping a little bit off and remeasuring, letting everything cool, strip off, a little measuring, so on and so forth. Now let's put it all together into a nice package. I prefer to create my wire-wound resistor in an open tubular form so that air can whisk the heat away more easily. I've chosen a standard writing pencil as my fancy high-tech form. But before we begin the process of wrapping our wire around the form, we should consider how we're going to secure the wire so it doesn't unravel when we let go of it. You could use hot glue or tape or epoxy. Epoxy takes a lot of curing time, so you probably need something to hold the wire in place while it cures. I'm going to use plain old cellophane tape because it's easy. I'll get some pieces ready so that they are available right when I need them. To make it easier to remove my resistor from the form, I wrapped some slippery paper around my pencil. and I taped it in place. Now I take my wire. This is my calibrated wire here. I leave a tail on here so that I have something to connect up to my circuit with, and carefully hold this in place while I wrap the wire tightly around my form. All of it, except when I get to the other end, I want to leave a tail on the other end for the same reason. I want some means of connecting it to my circuit. That's a pretty good tail. Okay, so we're going to hold that in place. We're going to take our tape and tape our windings in place. See, that just wants to come loose here. And we tape our windings in place. Now I'm putting the tape on lengthwise here, but now I'm going to take some tape and put it around it that way. And one more piece of tape. And there we have our resistor. We have our tails for connecting it up to our circuit. There we go. Just a matter of getting it started. And there's our beautiful resistor. We take the form out, and then we can take the tails of the tape and wrap them around into the ends of the resistor to kind of hold the ends of the resistor in place. And there we go. Our completed low-value resistor ready for final test. And here we are ready for final test. We've connected the current to the outside here. We've connected our voltage measurement here. And a note, from here to here is the resistance that we're measuring. Not out here, but from here to here. So when we connect this to our circuit, the value that we see as calculated from this point is the value of this resistor. So now we're going to turn up the voltage and the current and see what we get. Close enough, 5.55 amps and 101.7 millivolts. That gave us 18.32 milliohms. So I trimmed another 0.5 centimeter off of each of the insulations here, and we're going to retest. .57 amps, 100.3 millivolts. That gives me 18.007 milliohms. I'd say that we reached our goal, and that is the resistance from here to here, 18.007 milliohms.
Success! So now you can grow your own shunt or current sense resistors. You'll notice, however, that this process can get really cumbersome if you're shooting for higher currents like 50 amps. In these cases, you're probably better off buying a bona fide off-the-shelf shunt resistor. If you found this video helpful, please click on the like and subscribe to the channel. Thank you so much for watching. Until next time, Toodle-Oots.